give you an introduction to different types of microscope, and then I will give you a brief history about the invention of the scanning probe microscope. Then I will give you some ideas about the basic operation principles of the STM. That is, I will not go much details into the different types of STM, you will see it. But I will focus mainly on the basic modes of the STM. Then later I will move to some of our research activities. So in that one I will speak to you about some of our scanning tunneling microscope investigation of supramolecularly organized phenyl ethylene ethanol on surface 2D surfaces. That is and then I will also speak about the shape tuning or engineering of the supramolecular hydrogen bonded nanomaterials and their microscopic characterization. So first of all, I would like to tell you that I am not a physics guy, so I do not know how much you are going to enjoy my talk. Okay, so so everybody knows about microscope, right? Microscope is an instrument that is used to see the object that are too small to see for our naked eye. For our naked eyes, we know what is the minimum size that you can see. Does anybody has any idea? Do you remember it? Yeah, 0.1 mm. And so most of the things, if you consider the biological systems or at present it's nanomaterials or microscopic objects, if you want to see them or if you want to study them, you cannot use your naked eyes. So you have to magnify them. For that one, you have to use microscopes. So the name of the microscope originates from an ancient two Greek words, that is mikros, that is the meaning is small, and scopian. Scopian means to look or to see. Okay. So we have passed different eras like Stone Age and other Industrial Revolution and other eras. At present, it's a debate that we are in an era of nano era. Nano era means it's the creation of the functional materials and devices through control of the matter in the nanometer landscape. So you will see that the human beings, which is almost 1.5 meters, and if you can see with your naked eyes, when you come to the millimeters, up to 0.1 mm you can see with your naked eye, and when it comes to the micrometers scales, you have to use optical microscope. Whereas when you come to the nanometer scale, that is almost 1/8 of a human, 1/80,000, 80,000 of a human eye, you will not see, you cannot use the usual microscope to see them. So for that one, you have very nice stand. So if you want to study the materials in this regime, you have to use high-performing microscopes. Similarly, if you consider the development of the technologies, can you guys recognize any of these things? This is the first transistor developed in the Bell's lab, and this is the diode, Fleming's diode, first Fleming diode, and this is one of the very oldest form of our radio, transistor radio. I do not know if you have ever met this kind of thing. In fact, I have seen one with my grandfather. Okay, and this is the first computer, the developed computer, and the computer was like of the size of this room. Whereas if you come to the present state, these things you can recognize, right? The desktop, and then it moves to the very thinnest max air kind of laptop. At present, you can have the computers in the form of even your tablets, right? So all of these things are possible by reducing the size of the components in it one. So in 1941, you will have this vacuum tube based transistors and diodes, and as time passed, people have developed different types. At present, and then in 1960s, you can have the semiconductor based IC chips, which contains a lot of transistors, diodes, and capacitors. And now you will see something like this. Right. This is a printed circuit electronic board, which is the main part of this one. And even before the invention of the different, the highest level of microscope, the scientists used to dream about the future. So this was one of the famous scientists, Richard Feynman, and he used to speak about a new era, where in one of his classical talks he spoke about there is plenty of room at the bottom. So this talk was given at the annual meeting of American Physical Society at Caltech. So in that one he spoke. What I want to talk to you about is the problem of manipulating and controlling things on a very small scale, that is where you can manipulate with atoms and molecules. So the questions that he has put up, why can't we write the entire 24 volume of Encyclopedia Britannica in the head of it? At that time, visualizing such a thing was very great. But you know that at present it's almost achievable. You can have this kind of a pen drive, or even the size is very less, and you can store as much of the information that you want. So the question is, how do we write so small, or how do we process the information on a smaller scale? So in order to have this one, you need better microscope. So similarly, if you want to study the marvelous biological system, for example DNA and their functions, or either the physiology of your the way you are seeing it, everything needs microscopes. So if you look at the types of microscope, there are three different types of microscope. The first one is optical microscope, that everybody knows it. If you go to any usual lab, you will see that one. In the case of optical microscope, you have the very normal transmission-based optical microscope. And at present, you know that this year the Nobel Prize was given to an optical microscope, which is called a fluorescence microscope. And then comes the electron microscope, and today morning you have heard about the scanning electron microscope. And the other type of electron microscope is the transmission electron microscope. So I think tomorrow you will be having a talk by Dr. Manoj Ramasma. And the last and the latest one is scanning probe microscope. So if you consider the scanning probe microscope, you can have, this is a very vast topic actually. If you look into the different types of scanning microscopes by functions, you can have almost like 25 to 30 types of modes of are available with scanning probe microscope. And the first and most major one is the atomic force microscope, and you will have the scanning tunneling microscopy, and which will give you the morphology of the material. And in addition to that one, you will be you can have more like EFM, electrostatic force microscope, where you can measure the electrostatic forces, or it could be even the MFM, that is, you can study the magnetic force at a scale of nanometers. So there are different types of scanning type probe microscope. If you consider the advantages and disadvantages of different types of microscope, if I am going so fast, we can tell you. Or if you have any doubts in between also, you can ask. Okay. So the optical microscope. The importance of the optical microscope is that you can use it for even studying the living objects. There is no problem for that one. But the main problem is that it has very poor resolution. But today I cannot speak it like that because of the new advancement. That is where the new that this year Nobel Prize went, the optical resolution. That is usually, you know what is the optical resolution that you can have with an optical microscope. It is limited by the diffraction limit. Okay, if you use light, it comes to around half of the wavelength. The minimum wavelength light that you can use is 400 nanometer. That is too dangerous. But even if you are not able to, if you are able to use such a light, you will get a resolution of only around 200 nanometer. And that is only in the XY plane. If you go to the vertical z-axis, the resolution will be the micrometer scale. But at present, with the help of fluorescence microscope, you will be able to have broken this diffraction limit, and that is why it is awarded the Nobel Prize this year. And when coming to the electron microscope, the importance of the electron microscope is that you can have resolution, that is, you can even see the atoms with a 300 kV electron microscope. But the problem is that you cannot use it for living systems or very soft samples. One of the major problems is that in order to use this electron microscope, you need very high vacuum. And under such very high vacuum conditions, most of the living cells will die. That is one problem. And the other one is that you are using very high energetic electron beams. The impact or ionization that produced on the sample, most of the soft samples will decompose. Only for materials like inorganic materials you can use electron microscope. But if you reduce the electron volts, under electron volt you can see the biological system, but that cannot be used, that will not give you better resolution, and it cannot be used for living systems. Whereas if you consider the scanning probe microscope, it gives you the atomic resolution, very high resolution, that is similar to that of electron microscope, and it can be used for living systems as well. You can use it in the ambient condition. You can have a microscope here without having any vacuum. You can use that one. If you go to your optoelectronics department, you can see that one. And in addition to that one, okay, electron microscope also will give you some kind of material properties, but material properties that you can derive out of scanning probe microscope is very vast. It ranges from the mechanical properties to electronic properties to magnetic properties. Any kind of property you think you can study with the help of the scanning probe microscope. So the basic difference is, in the case of optical microscope, you have a light source that is used to illuminate the sample, and then you are having these optical lenses which magnify the sample. And in the case of electron microscope, instead of the light source, you are using electron source, and instead of these optical lenses, you have to use electromagnetic lenses. And in the case of transmission electron microscope, you will be studying the transmitted electron, whereas in the case of STEM, as you have seen in the morning, it is backscattered electron. Whereas if you consider the scanning probe microscope, does it use any lenses? So, in the case of scanning probe microscope, it does not use any lenses at all to magnify the thing. So, how it is possible to study then or to magnify things on an atomic scale? So, that is done with the help of a what is known as an atomically sharp probe, or you say atomically sharp tip, or it can also be called cantilever. Different terms you can call it. So, if you visualize how the AFM works, this optical microscope and electron microscope, it is similar to what you see with your eyes. You get a direct image. Whereas in the case of scanning probe microscope, it is like reading by a blind person. So how does a blind person read? He, instead of eyes, he uses his fingers, and then for them to read, there is this Braille system developed by Louis Braille, where you print whatever you want on a paper like this pattern, and then they sense with their fingers. So the basic principle of SPM, or that is SPM and AFM, is same as that of the Braille reading. In the Braille's reading method, reader uses his finger to detect the impressed characters. Whereas in the case of AFM, instead of finger, you use an atomically sharp tip to get the topography of the surface. So you have an atomically sharp tip that is almost equivalent to a blind person, and it tries to sense the surface with the hand, like a hand. And when you scan the sample surface with an atomically sharp surface, atomically sharp tip, depending upon the surface features, that is in case if you are having some height or depth, this tip moves up and down. And this movement of the tip, you can measure it, and that will give, and then you can plot it as a this z-axis movement of the tip with respect to x and y. That will give you the three-dimensional topography of the sample. So how do you do it is like a book reading. Book reading is called the raster scan. Raster reading. The raster method, what you do is first you read the first line and then come back to the first start of the line and then move to the next line and then move forward and read the second line and then come back and then move to this. So this is how the AFM works. So the tip first scans the sample surface on one line and then come back and then move to the second line and then read it and then come back. So you have this XY coordinate with respect to the up and down movement of this tip. That will give you the topography. So this if you have the line scan is called the slow axis, fast scan axis, whereas this line is direction is known as the slow scan axis. And the distance between the two measured points is known as the step size. If you collect more number of points, you will get a better highly resolved image. So the thing is that you have an atomically sharp tip and then it moves the sample surface. But to have this atomic resolution, you must be able to move either the tip or the surface with an atomic precision. If you usually to move the atomic the samples, you can use motors, but the resolution of the motor is very less. So in order to have the atomically resolved resolved movement, there comes the importance of the piezoelectric substance. You know the piezoelectric substance. When you apply a voltage, or in certain case of crystal, if you apply a pressure to the system, it develops a voltage. Similarly, if you apply a voltage to the same kind of crystal, it can either extend or contract. And that is movement will be in the nanometer regime. And usually there are different types of scanners. There are flexure scanners and tube scanners. And you use three different pieces for the X, Y and Z movement. That is how this AFM works. You have this atomically sharp tip and movement is done with the piezo scanners. Okay. If you look into the story of the invention, the story started in around 1971. It was with Russell Young, who was a scientist at National Bureau of Standards. So he tried to design some form of this scanning probe microscope, and this is one of his designs where he has this piezo scans, vertical scan. And then instead of, and here he has a similar to electron microscope, he used an atomically sharp tip, which is act as an emitter. And then to adjust the sample distance, he used something like a screw gauge arrangement. So that was the first type of microscope he developed. But the problem with such microscope was the resolution was around 200 angstrom, that is around 20 nanometers. So that is he was never able to achieve the atomic resolution. But he realized certain things. That is how the things work in science. You try to do something and it may not work, but then if you put up this idea, people will take it up. So what he understood that instead of using this as emitter, you can use instead another effect called the tunneling effect. Right. So what is tunneling effect? If you bring two conductors very close to each other in the range of few angstrom, depending upon the work function, the electrons will jump from one electrode to other, even if there is no contact between the two. And This tunneling you can also induce by applying a bias voltage also. If you apply a bias voltage, that is if you are modifying this electric potential. So the interesting thing about this tunneling effect is that it is inversely proportional, inversely, and the current or the resistance is exponentially proportional to the distance between the two, or the current will be varying in inverse exponential rate. So if you change the distance between the two conductors by a few 1 angstrom, the response that you get, current response that you get will be almost 10 times. But even though he knows this principle, he was not able to put into the practice, mainly because there are some problems when you want to develop something. Always you have to find how to engineer the things. So one of the problems was his project got terminated in 1971, so he was not having enough funds to carry out his project forward. And the other problems he found out was there is the stability to maintain the gap between the surface and the chip of order of few angstroms. There was no technology at that time available for that one. And a technology to position and scan the probe over the surface with sub-angstrom system, that is piezoelectric computer is there, but how to scan that one was not there. And methodology to bring a sample and starting from very high. So when you start air from the tip and the substrate will be the distance between will be few millimeters to centimeters. So how, from that distance, how do you bring to a very close distance of few angstroms? So these were the problems that he has faced. And later, two scientists from IBM laboratory, they took up this challenge. This was a senior scientist in his IBM laboratory, Zurich laboratory, and this guy joined as a postdoc with him. And then this professor gave him the job of making this scanning probe microscope, and there they succeeded in that one, and that was and for that invention they have been awarded the Nobel Prize in 1986. So this is the picture of their atomic force scanning tunneling microscope. They need the first developed atomic force microscope, scanning tunneling microscope. You can see the size. You can hold the microscope in your hand. Whereas if you want to have an atomic soluble TM, you need few meters of length. And these are a few of the images that they have collected. This is silicon atom, silicon substrate atom, and this is a coral structure made up of iron atoms. So what they have found is that you can use this, what they have succeeded in all the problems that Russell Young was facing, and then they were developed to succeed in developing the microscope. Later these people used it for studying different types of substances. One of the first thing was how do we see the porphyrin? I do not know. Since this is a physics background, basically porphyrin is an aromatic molecule where it has a more electron density in this kind of ring-like structures. So whenever there is a higher electron density, the tunneling current will be very higher, and in the case of AFM, you see that one. Similarly, if you consider certain tasks like if you want to characterize different geometries of Fullerene primers, there is no other technology available present. Because if you consider if you want to take a mass spectrum, all of these three isomers will give you the same mass. If you take the NMR or IR, everything will give you the same result. So the only thing is you have to make such system. And if you look into the TM mostly you will not get this because of the carbon atom. The only thing that you can use is airflow. And you can see beautifully how this is 90 degrees, this one they get 90 degrees, whereas it is changed 108 and here it's even 120. So, imaging such systems are possible. So that is, SQL will give you atomic resolution. But there are different limitations for the scanning tunneling microscope. One of the, the basic principle of the scanning tunneling microscope is that it uses tunneling current as a feedback signal. It monitors the tunneling current between the sample and the tip surface. So, in order to have the tunneling current, you need to have the substrate conductivity. So, if you have a non-conducting material, you cannot use scanning tunneling microscope for imaging applications. You will fail it. So, in order to overcome that one, people start. Initially, these two guys initially thought of that one. They were succeeded in that one. So there they come up with this new mode, that is atomic force microscope. And in the case of atomic force microscope, instead of tunneling current, they use monitor the forces between the tip and the sample surface. They monitor it. If there is an attractive force, the tip will bend down. If it is a repulsive force, the tip will bend up. So, if you are able to measure this bending or deflection of the tip, you can get the surface morphology. So with that invention, since it can be used for any kind of substrate, whether it's conducting or could be non-conducting or semi-conducting, whatever, because the atomic forces will be always there, because all the materials are made up of atoms. And usually the cantilever, the tip is held at the end of a thin, and this is how the AFM tips look like. If you go and see the optoelectronics, they can show you the tip. But you don't see this one, you will see something protruding out this one. So basically it is having a flexible beam called cantilever, and at the end of the cantilever you have a triangular shape which is pointing up. And usually there are two different types of materials people use. One is silicon nitride, and that is very stable one, and it can be used for hydrophobic substances. And the other one is silicon tips, which is very sharp but it's hydrophilic, and it can be used for biological applications. And if you want to study other properties, you usually coat it with the type of material that you want. For example, if you want to study the electrical conductivity, you can coat this chip with an gold or platinum. So this is how you make the chip. Usually it is done with, there are different techniques. One of them is microlithographic process, where you have a silicon wafer and you make a pit in it, terminal pit in it, and then you deposit silicon nitride over it, and then you can lift it off. So in the case of atomic force microscope, the forces between what we are going to monitor is the force between the atoms, between the atoms of the tip and the surface. So if you consider these two atoms very far apart, there won't be any interactive forces between the two atoms. Whereas if you bring it close, at a certain point they start attracting because of the van der Waals interaction. Usually the attractive forces are van der Waals interaction, and when you bring it so further close to few angstroms, less than an angstrom close to each other, then these electron clouds interact with each other and then they start to repel each other. So that is the interatomic forces that you are going to monitor. And if you, this is what I will say, if you bring, okay, you can consider this as a tip and this is your surface, and you start bringing down this one, okay, and then you start measuring the forces. You can see that at very large distance there is no bending of the tip. Whereas when it comes to this attractive region, that is this van der Waals region, the tip starts to bend, and closer and closer you move, the tip will be bending more and more. And after this van der Waals region, it starts the repulsive region. And the repulsive force increases exponentially with the distance. So, depending upon the type of force that you are going to use, there are different modes of air pump. If you are going to use this repulsive force, that is called the contact mode air pump. Whereas if you are going to use this attractive force, that is van der Waals interaction, then it is called the non-contact mode. And in between, we can use intermittent contact mode. We will come back to that one. Okay, so that is simple. This is an actual experiment, that is a theoretical curve. So this is like you start from here. This is how the atoms move. Okay. When you bring it down, this is your starting point, that is the green one. And then if you bring close to each other, then start this van der Waals interaction, and then the tip bend to the snap to the surface. Okay. And when it reaches this one, and then further you decrease the distance, the tip will start bend upwards. Okay. And then you try to withdraw this tip. After reaching here, you try to withdraw the tip from the surface. So, due to this contact force, the tip starts bend to the normal stage, and after the normal stage, if there is an interaction between this tip and the surface, that is what we call the polygraph interaction or atomic interaction, then the tip will start staying for the. For example, if your tip is positively charged and your surface is negatively charged, then they will attract each other, and then they start to, then the tip starts bend downwards. Okay. And still if you move, and when the forces between this tip and the substrate over forces exerted by the bending of the tip, then the tip will retract. So, like that, you can study what is the interactive force between the tip and the sample surface. So, this is usually the force you can kinetic motion of the cantilever you can approximate like a spring, and it is having you can approximate the Hooke's law, that is force exerted on the tip will be proportional to the minus k, where k is the spring constant you get in this region. And the separation, the change in the length. So the problem is that in the case of tunneling current, you are having exponential relation, whereas here you have an proportional relation. So the resolution also will change accordingly. You cannot have the same resolution as AFM cannot have the same resolution as scanning tunneling microscope, but instead you can use it for studying any type of material. So, the questions at that time asked were how to monitor this movement of the tip. That was the question people asked. And you see this in the case of STM, people showed that you can use this tunneling current to monitor the separation between these. So initially they thought, that is the spinning that you guys, spinning at all, they thought why don't we use this conductive cantilever and then use an STM tip on it. That is, when the tip moves down, the separation increases, and the tunneling current between this STM tip and the cantilever, not the surface. That is one thing you have to understand. Increases and the tunneling current decreases. Similarly, if the tips move up, the separation decreases and the tunneling current increases. Okay, so this is the first type of AFM developed, but the problem is that how are you going to use such instrument? The problem was one of the things is that you have to align an atomically sharp tip with an on the surface of the cantilever, and the size of the cantilever is few micrometers. So how are you going to do it? And Then there is the problem comes thermal drift. If there is a temperature, then the cantilever or the chip can change its position. So there also the dynamic current changes. I think I will move a little more faster. So people thought of how to, instead of studying what are the different techniques that you can use, and people develop what is called as optical detection, where you use an laser system and then position sensitive photodiode detector. Position sensitive photodiode detector means depending upon this, see, if you are going to have different angles, the laser will be directed towards different points in the position sensitive detector. And the importance of this one is that you can accurately measure with the help of wires, either in the terms of voltage or current. For example, if it is falling in this region, the current this voltage will be 0, whereas if it is falling here, the voltage could be like 1 volt, could be plus 2 volt, like that. So, depending upon this signal, that is where this laser spot falls, you can measure the movement of the chip, and you can measure this with an accuracy of few angstroms. The displacement can be measured as small as 10 angstroms. So with that development, now new AFM, all of them uses this laser technology and this position sensitive detector, and now it's very easy for it to, you have two screws which you can move it, and then you can align it with the paper method, and then you can align it, and then you can use it one. And you can use it for imaging different materials, like even you can use DNA. So this is, if we come to the basic modes of the AFM, I told you there are 3 different modes. One is the contact mode, the other one is non-contact mode, and the last one is the intermittent or tapping mode. In the case of contact mode, the forces, the atomic forces between the chip and surface will be repulsive, and you are operating in this region. So what is it? It means that your chip is always in touch with your surface, and you know that it is an atomically sharp chip. What will happen if you scan your hand with a sharp knife? So similarly, the sample also gets damaged if you are using soft samples. That is the problem. Whereas in the non-contact mode, you are operating the chip at a very large distance, and you see that the forces are very small, that is 2 to 3 kilojoules per mole, and that forces are very big, and if the separation is very high, you can see it's how it is dying out. Initially you have a good response, when as the distance increases, the response also changes. So that will not give you better resolution. So instead of that one, if you are able to use this one, in between this one, you can have better resolution as well as less sample damage. And for that one, people invented this technology called the tapping mode. In the case of tapping mode, what you have is your chip is always oscillating like this. And then when it is oscillating in the air, it will be having a frequency, and you can consider it like a sine wave or cosine wave, and it will be having amplitude and frequency. And when it starts touching the surface, either this amplitude or the frequency changes, and that will be proportional to the distance between the chip and the surface. So that is the intermittent contact or the tapping mode. So in this contact, this is very light tapping, so you will not get the sample damage in this one. But at the same time, you get a better resolution. Okay. So there are, even with the basic modes of AFM, there are different things that is possible. One is called lateral force microscopy. In addition to this topography, that is the morphology of the system, you can measure if there are 2 types of materials in your system. One is rough and the other one is smooth surface. If your substrate surface is a smooth, then the chip will be, the laser it will be always like this when it scans, and the laser spot will be in this one here in the middle. Whereas if you scan the rough surface, there will be always an interactive force between the roughness, friction force between this chip and surface that causes the chip to bend a little bit. So depending upon that one, the laser spot will be moving in this quadrant. So if you are able to do that one, you can characterize the surface whether it is smooth or rough surface. Similarly, if you consider this tapping mode, the tapping mode, there is always this oscillation of this chip, and you consider if there is no interaction between the chip that is attractive or repulsive interaction between your chip and the sample surface, there is not much the applied frequency. You apply a frequency to the chip to oscillate it, and the chip oscillated. There will be always a constant phase of the amplitude and frequency for that one. Suppose if there is an interactive force between this chip and this sample surface. In that case, your the chip, after touching the surface, it lags a little bit compared to your applied frequency. So there is a lag between the phase of the wave, right? The amplitude will be coming at a later stage. So if you are able to monitor this one, you can characterize different types of material. For example, if you consider the wood pulp fiber, you can, this is the height image where you don't see much information. Whereas if you consider the phase image, you can see very detailed image of this contrast between these different types of fibers in this wood pulp. So that is possible. Okay, this I will skip. This is about force measurement. So basically, you can study intermolecular forces. That is what I say. And in addition to that one, see, addition to morphological characterization or property measurement, you can also use this chip for lithographic purpose. You can use this chip to pick an atom from the sample surface and deposit it in a place that you want. That is, or you can also use it as like a heat pen, where you can coat it with different types of materials, and then you can scan it over the surface and you can deposit it in a place that you want. So, or even you can use heat it, this one, and you can write it on a polymer substrate. So different types of possibilities are there to manipulate the materials. So now I will move to some of our research activities. So this mainly focuses some of the chemistry aspects. So I will try to reduce as light as possible. If you do not understand, please let me know. Okay. So this is what actually started during the my PhD time. At that time, it was in 2000. Almost 2005, I think, that we bought a new air pump, and I have been asked to work with air pump. Okay, that is the only job given to me. So I studied this instrument, and then I studied different modes of that instrument. But if you consider like a chemist me, my synthetic capabilities to synthesize molecules is very less. If I want to make molecules, I have very little efficiency in doing it. But instead, I usually like to study the instruments. So at that time, in our group, that is Dr. James P. used to make a lot of molecules. Three benzene rings connected with a triple bond. This is called phenylethylamine. And these molecules, he used to make this molecule for studying the photophysical properties of photon emission and how their charge transfer occurs like that. And these kind of molecules, you see, if you consider fluorescence, they are very highly fluorescent molecules. Even in the solid state, you get quantum units of the order of 1. That is, if you give 100 photons, you will get 100 photons out. So what I thought is that, why don't I use some of these molecules to study certain things in that one. So I selected this molecule, which is having an alkyl chain, and then I try to deposit it on the surface like a simple solution deposition technique. And then I try to, if you ask me, this is not an easy job. It almost took me 6 months to get this first image on this one. So what I saw is that a lot of line-like structures are there on this surface. So the scale, you can see that this is 15 nanometers, so the whole surface will be like 45 nanometers, 45 nanometers square. So when you want to have better resolution, you zoom into that one in a real time. That means here you are measuring 45 nanometers square, whereas here you measure it in 15 into 15 nanometers square. So at that time, these line-like structures appeared like a lot of bright spots are arranged in an one-dimensional pattern. So I was not happy with that one. I still reduced that one, and what I could see is rod-like structures arranged in a skewed one-dimensional pattern, and then they maintain a constant distance between them. So this is what I found. So I was thinking what it could be. So if you consider this molecule, I told you this is 3 benzene rings connected with triple bond, and if you do a molecular orbital calculation and try to map the electron density, you can see that the electron density will be maximum along this direction, and this is alkyl chain which does not have any electron density, and it will not be conducting as well. So what you see is these bright spots correspond to these central phenyl ethylene core units. So if you start arranging the molecule, you can see that all of them are having same length and same separation. And what we found is that this is not the only surface that we are getting. We are getting different types of arrangement. And then what we found is that there are 2 different things. One is that there is an arrangement in this direction, and there is an arrangement in this direction. Okay, that is we call A strip and B strip. And if you consider the distance between these 2 units, either here or here or here, that is always 1.3 nanometer. So why it is coming 1.3 nanometer? So that is one of the questions that we were asking at that time, and that was a period when Dr. Joe Thomas told me to visit NIIST Bangalore to study a little more detail about the scanning tunnel microscope. And to be fortunate, at that time one of their PhD students was also working with a similar molecule, and but their aim was to study their fluorescence properties in the solid state or crystal fluorescence or the crystal fluorescence, and they were analyzing the crystal structure, and I was standing nearby to him, and I saw that when he was doing the analysis, there are some kind of patterns coming like this. And then I asked what is the distance between these 2, then that is coming 1.3 nanometer. So we thought that similar to the crystal structure, on the 2D surface also similar things will be happening. So how do we know that this distance is maintained by the interdigitation of the alkyl chain? So how do you make sure that that is alkyl chain? The only thing as a chemist I can think is increase this length of this alkyl chain. So now here it is C6, now it is moved to C12. So in that case, when you take the STM, you can see that the pattern is same, but the distance has changed from 1.3 nanometer to 2 nanometer. So that distance is maintained by the interdigitation of the alkyl chains. Okay, so this is how the mechanism. So what we thought first, the alkyl chains interact slightly, and then they form this pattern, and then there is an interdigitation. Okay, and then we also did molecular orbital calculation of this model, and we got similar results. So the other thing was there is a interdigitation of this phenyl ring. So to say that one, I selected another molecule which is having hydroxyl group. Hydroxyl group means it can form hydrogen bonds, like in the case of water. So in that case, what we found that instead of interdigitation, they form an end assembly, and even you can see the oxygen atom. And later, fluorines nowadays is a very interesting molecule because it's applied in solar cell applications and all. So at that time they are having this kind of a dumbbell-shaped molecule which is having phenyl-4 and fluorines at both ends. So I took this molecule and tried to organize it, and then I got this wire-like structure. But you have to be very careful when you do this one. Usually you do this on a HOPG surface, and then you come up with a lot of these kind of features. But when you zoom into that region, you can see that that is nothing but the step edge. Usually when you peel off one layer of HOPG, one layer will be sticking there, and that will give you the same arrangement. But when you zoom in this region, you can see bright spots there, and the distance between two spots will be 1.75 nanometers, and the size of this bright spot is same as of the polar intensity. So we were able to get one-dimensional arrangement. So then I moved to, after my PhD, I moved to postdoc in Italy. So at that time, we thought, okay, we will continue with the same type of molecules, but then I will not do the STM. I will see whether I can use this material for engineering a little more higher version of the nanomaterials. So that we can organize these molecules into different types of nanomaterials like spheres, vesicles, or what is called ring-like structures or fibers like that. So for that one, what we have selected is an force between you have to optimize the force between the molecules, and we selected this hydrogen bond. The hydrogen bond, it's a very powerful intermolecular interaction, and that is where all your biological processes happen. Even if you consider this water, the water is liquid only because of hydrogen bond. And if you consider this strength of this hydrogen bond, you see that it's come around 120 kilocalories per kilojoules per mole, whereas your van der Waals force, you can see that that is coming to 2 kilojoules per mole. And when you consider the DNA always have a double helical structure, and it's a base pair. That is only because there are a certain way of interacting the molecule, what is known as complemented hydrogen bond. So only two types of things come each other. So we selected such moieties from biology, and then we made this molecule, and then we started trying the organization of the molecules in solution. That is, one thing you can do is you add a bad solvent into that one. So usually for this molecule, this is a highly polar molecule, and then this polar solvent, you can see that the absorption spectra is not at all affected. I do not know how much you understand it. Okay. But when you take it in less polar solvent, you see that your absorption spectra is redshifted. That is mainly because only in that solvent you can see it, and in the case of even if you take the fluorescence, in the fluorescence also you can see that it is more redshifted. That is, all other cases is coming around 425 nanometers, whereas in cyclohexane it comes around 475, and in water also it comes around 500 nanometers. So these are the two solvents that you can find where it is undergoing redshifted features. So if you take this one, this is a colorless substance, whereas if you take this one in this solvent, the color changes to green. That is how you can visually see it. And then what we thought is that usually this is basically due to the interaction of the two molecules. When they come close to each other, there is something called pi-pi interaction. By electron cloud interacts, like you have these atoms and molecules like that. If you consider the energy level, the atoms will be having higher energy separation between the orbitals. When it comes to molecules, the separation will be decreased like that. When the molecules interact, their electron cloud interacts with each other, and then their energy level, that is this, in the case of physics you say conduction band and valence band. In our case we say this highest occupied molecular level and the lowest occupied molecular level. So these are the two terms that we use. So that separation decreases, that is why this undergoes a redshift. So that is made clear by increasing the temperature. When you increase the temperature, you give a lot of energy to the system. So the all these molecular interactions take and then comes to the individual molecule, and then it shifts to the, there is a blue shift of this absorption spectrum when you increase it, and finally you reach similar to that of the other solvents. So you see that they are forming, they are undergoing aggregation, and what you see is the formation of nanomaterial. So we characterize this nanomaterial with confocal fluorescence microscope. When you see luminescent nanomaterial, and then we took helium, and then we also took here from where you see this kind of spherical structure. Okay, I will not take much time. So this is mechanism. Then we thought whether we will be able to modulate the organizer. So there we took another molecule which is having the complementary hydrogen bond. This is complementary to this one. This will form hydrogen bond with this one. This will form hydrogen bond with this one. This will form hydrogen bond with this one. So basically, when you do that one, you get a, similar to that case, you get a new band which is absent in both the cases, and that we add to this 5 pi stack. Okay. So when you do the wide field microscopic characterization, what we found is a ring-like fluorescent material. And similarly, when you do it TM, the case of TM also you see ring-like structure. But if you consider this fluorescent image as well as the TM image, both of them gives you ring-like structures. But in reality, there are two options for that one. One is, it is in reality itself it's a ring-like structure, or it could be hollow sphere. And you are monitoring only the ring. Okay. So in order to understand that one, you need AFM, and when you do the AFM, you don't see any ring-like structure, but instead you see spherical structures. So this is possible only if it is a hollow, or what you call vesicular structure. So that is how you characterize that one. So then what we thought is whether we can something missing here. Whether we will be able to engineer further. So first we have nanoparticle out of this one, and then you have vesicle, and then we thought whether we will be able to develop fibers for this molecule, and then whether we will be able to control this one. And then for that one we use a capping ligand where it ends here and caps it. So you do not have polymerization, further polymerization. So that is what we did, and what we see is that when you use the linear type of molecule, you get a linear polymer and it forms a nanofiber. And similarly, if you are going to change the molecular geometry to pen-like structure, instead of linear polymer or fiber, you get twisted fibers. That is how you change the nanoscale morphology with molecular structure. And if you are going to cap it with a different molecule, you get the size is reduced to nano-rod-like structure. So by playing with the molecular geometry, what I want to show you is that you can change the morphology of the nanomaterials. And then, okay, I will not. So what we thought next was whether we will be able to take advantage of this one for any further application. So one of the applications that we thought was, can we use it for the solubilization of carbon nanotube? You know carbon nanotube. Carbon nanotube is a very, like fluorine, it's another interesting molecule. But the problem with the carbon nanotube, and it has very good electrical and mechanical properties, and it is found application in different sectors like sensors, electrodes. You can use it for electrode for solar cells, and it is used as catalyst, or even you can replace your nerve with carbon nanotube. So there are different types of applications. But the major problem is that when you take it, it is like a junk black powder. You cannot use anything out of it. That is the problem. For that one, you have to get individual carbon nanotubes. So how do you do it? So we thought whether we can use our molecular units for that one, and what we thought we will make supramolecular polymer and interact with carbon nanotube. And then what we found is that when you take this molecule along, this is how the carbon nanotube looks like if you want to take it in solvent. It is a black powder and it does not dissolve in any of the solvents. So you cannot use it for any application. But when we use it with our polymer, we can see that the carbon nanotube is completely dispersed into the system, and it is like any other system you can deal it with. And then you can also break that interaction by adding a different solvent, that is we call DMSO, and then you can precipitate out your carbon nanotube. So that is how we study by absorption and emission, where you see the formation of a new band in a similar case. So what we feel that there is a formation of supramolecular polymer around the surface. Okay. And then we characterize it with different techniques like XTS, where you get the nitrogen signal in the case of this solution, whereas in this case you do not get a nitrogen signal because of the absence of the molecules. And sorry, this is a little unclear. And when you take the TM, you can see that the carbon nanotubes are well dispersed. This is some contrast differences there. I am sorry for that one. But you do not see any further information on that one. How this is arranged, on the, how this is made possible. So in that one, we took it up with the SPM, scanning tunneling microscope, and we investigated the scanning tunneling microscope, and what we found is that these fiber-like structures are carbon nanotubes. And on the carbon nanotube, if you look at trace, you can see there are a lot of ups and downs, and that corresponds to our supramolecular polymer. And similarly, if you do the AFM, there are different types of materials that we use in all this kind of supramolecular thing. You can see this carbon nanotube contains a lot of packed with molecular unit. So this is I finished it here. So I believe that I have showed you some introduction about the SPM and introduced you some basic principles about scanning probe microscope, and I showed you how it can be used for molecular imaging, or how it can be used for imaging different nanomaterials. And these are the people who has inspired me or affected in my life a lot. That is, this is Professor George Thomas. The first part of my talk he introduced me into this field of scanning tunneling or scanning probe microscopy. And then this is my postdoctoral professor, and this is my postdoctoral collaborator, Dr. Nicola Arnold, and this is Dr. Davide Bonifaci. And this was one of my best friends who used to make molecules for me. At that time, she made all these molecules and gave to me for this my investigation. So that was another person. And there are other people who helped me. That is Dr. C.H. Suresh, who did this molecular calculation. And then for the GU I told you, I went there for studying the SPM and all these molecular interactions, that is crystal practice, everything I studied from this. And there are a few other people, Dr. A.R. Ramesh, Dr. P.V. James, Dr. Vinod George, who gave me these molecules for study. They made these molecules. And this is Dr. Abdul Bilbak. He was a PhD student. He used to help me in photophysical measurement. And this is my present group, Mr. Arun Gobi. He is from, these are the people going to influence me next. Okay, so this is Mr. Arun Gobi. He is from Ernakulam, Mr. Vidya Sarmi from Calicut, Ms. Sajida from Trivandrum, and this is Ms. Raihamor from Idukki. So all of them work on different types of problems, but I do not share that one today. And finally, I thank you for. So if you have any questions, you can ask me. I know that I run a little fast because of the time constraints. But still, if you want to have any clarification, you can ask right now, or if you go to our website, you can see my email ID.